Welcome to section 4.6. Today we're going to find a basis for row A, col A, and null A. And we've already done null A and col A. We talked about that in section 4.3. But row A is new. And so here are the definitions at the top here. Col A of a matrix is the space spanned by the columns. Row A is the space spanned by the rows. And null A is the set of solutions to AX equals 0. So to find a basis for null A, find a basis for null B, where B is any echelon form of A. This was from section 4.3. And the reason why you can use null B is that row operations don't change the null space. We also found a basis for col A in section 4.3. And in this case, what we did is we reduced A to B and then used the columns from A that corresponded to the pivot columns of B, but we had to choose the columns of A. This is what's new. Row A. To find a basis for row A, you're going to use the non-zero rows of B. Okay? Non-zero rows of B, not of A. Elementary row operations do not change the row space, and they do not change the null space. They change the column space. But even though they don't change the row space, they will change the linear dependence relationships amongst the rows of A, so that's why you have to use the non-zero rows of B. We'll do an example on the next page of each of those, so don't worry about that. Rank plus nullity theorem says that well, first of all, the definition of rank of A is the dimension of col A. And the nullity of A is the dimension of null A. And what the rank plus nullity theorem says, this part of it, it says, if you look at the number of variables in AX equals 0, which is n, for an m by n matrix, there would be n variables. Those variables either have to correspond to free variables or leading variables. You're either a pivot column or you're not. So the number of columns has to add up to be, between pivot and non-pivot, has to add up to be n. The first part of the rank theorem says that the rank A is equal to the rank of A transpose. And that's basically because the rows of A are the columns of A transpose. And so if we go back up here, rank of A by definition is dim col A, but by the rank theorem, it's also dim row A. All right, so let's put some of this to work. The first example is just dealing with some of the definitions. A is a 5 by 8 matrix, so A is going to map R8 to R5. Remember, the dimensions swap. And the rank is 5. The nullity of A. The nullity of A is 3. And that's because the rank plus the nullity has to be 8. N equals 8. And 5 plus 3 is 8. The rank, we're told the rank is 5. Dimension row A is the same as dimension col A, which is the rank, which is 5. Rank of A transpose is the rank of A, which is 5. Okay, now the more interesting questions. Is col A equal to R5? So take a look up here. A goes from R8 to R5, and col A lives over in R5. So col A is a subset of R5. It's actually a subspace. And it's a 5-dimensional subspace of R5. So the answer is Yes. Col A is all of R5. I'm using this fact here. The only n-dimensional subspace of Rn is Rn. So the only 4-dimensional subspace of R4 is R4. The only 5-dimensional subspace of R5 is R5. Is AX equal B consistent for all B? Yes, since Col A is all of R5. And we had a result in section 4.2 that told us AX equals B is consistent for all B if and only if Col A is all of Rm. Okay, let's do some computation examples. We're given A and its row equivalent to B, and we want a basis for row A. So if you look in the chart on the first page to find a basis for row A, you take the non-zero rows of B. So that's just easy. You can just write them down. 1, 0, -3, -6, and 0, 1, 0, 0. Your book, when you do your my math lab homework, your book will have you write those as columns, but I'm going to write them as rows. All right, basis of Col A. Well, the pivot columns of B are columns 1 and 2. So a basis for Col A is going to consist of the first 2 columns of A, not of B. -1, 2, 1, 2, -5, -3. So note that the rank of A is 2 because that's the dimension of the column space, because the basis has 2 elements. Okay, basis of null A, we can solve Bx equals 0 since that's equivalent to Ax equals 0. I've already augmented B with the 0 vector. So we can see there's 4 variables. Let's start at the bottom. X4 is free, I'll call that T. X3 is also free, call that S. X2 is 0, and X1 is 3S plus 6T. So our solutions look like S times 3010 plus T times 6001. So basis for null A consists of the 2 vectors there without the S and the T. 3010 and 6001. And notice the nullity of A is 2. That's the dimension of the null space. And sure enough, rank plus nullity, 2 plus 2, is 4, which is the number of columns of A. Okay, now some thinking problems. The first one I've already answered for us. And the first one just points out that whether you're talking about AX equal B or AX equals 0, free versus leading variables will be the same. So if AX equals B as 2 free variables, that means that when you reduce the augmented matrix A with B, there will be 2 non-pivot columns, in this case here and here. Well, when you reduce AX, the matrix A augmented with 0, you're going to have the exact same 2 non-pivot columns, 2 and 4. So pivot columns versus non-pivot columns don't depend on whether you've augmented with 0 or with B. So to that end, let's answer the next question. Suppose AX equals 0 has 1 free variable. Can AX equal B have a unique solution for some value of B? No, since AX equals 0 has a free variable, so AX equal B has 1 free variable also. So you can't have a unique solution if there's a free variable. That gives you infinitely many solutions. Okay, next one. What is the largest possible rank of A if A is 4 by 3? Well, the rank of A is the dimension of col A. We've only got 3 columns, so the maximum rank is 3. Now let's turn it around. Let's do a 3 by 4. Now there are 4 columns, but the maximum rank is not going to be 4 because the rank A is the dimension col A, but it's also the dimension of row A. And there's only 3 rows. So the maximum rank is 3. In general, if you have an m by n, the max rank is going to be the minimum. Max rank is going to be the minimum of the 2 numbers m and n. Okay, next one. Suppose A is 9 by 12. What is the smallest possible value for the nullity? Well, the max rank is 9, because that's the smaller of 9 and 12. But rank plus nullity has to equal 12, so the min nullity is 3. That's the smallest the nullity could be. All right. Couple more of these. Suppose we have a 5 by 6 and it's got 4 pivot columns. So A is a mapping from R6 to R5. It's important to know where you're going from and where you're going to answer these questions. And the rank is 4 because we're told there are 4 pivot columns. Okay, what's the nullity? Well, rank plus nullity has to be 6. So the nullity is 2. That one's easy. Is col A R4? Well, col A lives inside of the target space, R5. So col A in R5 is a 4-dimensional subspace of R5. I know it's 4-dimensional because that's the rank, and the rank is the dimension. So the answer is no. A 4-dimensional subspace of R5 could not possibly be R4 because R4 is not even a subset of R5. The best you can say is col A is a 4-dimensional subspace of R5. Okay, is null A R2? Well, you have to know where null A lives to answer this question. We know the dimension of null A is 2 because that's the nullity, but the null space lives over here in R6. So null A is a subspace of R6, and it's a 2-dimensional subspace of R6. So the answer is no, that couldn't possibly be R2 because R2 isn't even a subset of R6, so it couldn't be a subspace. Let's do one more like this. A is 7 by 11, it's got 7 pivot columns. So A maps R11 to R7, and we're told the rank is 7 because there are 7 pivot columns. Is col A R7? Now the answer is going to be yes. And here's why. Col A lives inside of the target space, which is R7, and is a 7-dimensional subspace of R7. There's only one 7-dimensional subspace of R7, and that is R7. And that's from this fact in red, up here, the only n-dimensional subspace of Rn is Rn. Okay, is null A R4? Well, the rank of A is 7. The nullity is, 4 plus 7 is 11. So the nullity is 4. That means null A is a 4-dimensional subspace. The question is it R4? Well, you have to know where null A lives. Null A lives in the domain. So the answer is going to be no. Null A lives inside R11, is a 4-dimensional subspace of R11, but that's the best you can say. That doesn't make it R4. It just makes it a 4-dimensional subspace of R11. If it were an 11-dimensional subspace of R11, then the answer would be yes, it's all of R11. But that's not the case. Okay, so if you think you might be getting the hang of it, do these practice problems, pause the video, do these practice problems. I have the solutions at the end. And then for the next half of this, I'm going to stop this video here, and then I'll pick up a second video for the rest of the lecture notes.